interesting question about the result. That was one of the rare cases where the result was essentially digital. Mice on PUFAs did not have any indication of the disease at all. They were a totally normal, healthy phenotype.
Hi, this is Tucker Goodrich, and I am back today to discuss the topic of deuterium. The last time this came up was with John Speakman, and he's a world expert in the topic of using deuterium to measure metabolism. And today I am honored to be joined by Mikhail Shchepinov, who is a research scientist who has looked into using deuterium as a therapy. Specifically, he has just written a book, Breaking the Chains of Aging, in which he looks at using deuterated lipids, specifically linoleic acid and other polyunsaturated fats, to alleviate some of the diseases of aging. Aging is a topic I think is really fascinating. I think most of the, aside from, eat a good diet, which even people argue over what constitutes a good diet, I think most of the therapies that are directing towards aging are somewhat lacking, things like rapamycin and metformin. This is a bit more interesting, however, and I would like to explore this topic in this podcast. Dr. Shchepinov, if you could introduce yourself, give us a little bit of background and how you got interested in this research topic.
Thank you, Tucker. Yes, I'm Misha Shchepinov, and I've been interested in age-related things and aging and what could be done about it since I was at my early years in university, I suppose, if not earlier, if not at school. I am a chemist by training. I did my PhD in Moscow. I then worked in Oxford University for quite a few years, focusing on DNA-based DNA chemistry. And I kind of gradually migrated into chemical aspects of genomics and proteomics. And at some point, I had to use stable isotopes, deuterium and carbon, to make unique shifts in mass spectrometry of molecules, which will not be affecting any chemistry in any way, but will be giving unique signatures on during the mass spec experiments. And my evening reading before going to bed reading was usually to do with aging. So one day, 20 years ago, actually, this year, it just clicked. And because I was reading about oxidative damage to biomolecules, amino acids, DNA bases, lipids came distant third, actually, on that list. I was mostly initially concerned with amino acids and DNA. So it just clicked that when a reactive oxygen species comes and abstracts, rips out an hydrogen atom out of a molecule, the rate-limiting step of that process is hydrogen abstraction. So if that hydrogen were in its heavier version, deuterium, then the reaction would be going on slower. So that was the key observation, if you will, or revelation, and that happened when I was thinking about lysine. So I then did some search around amino acids followed by DNA bases, applying the same kind of idea, the same concept to these molecules. And then only much, much later, after discussions with Aubrey de Grey, did I start focusing on lipids. The common denominator between these three groups of molecules with regards to this deuteration approach is the fact that they
let's before we get too much into mechanics, just a little bit more background. So,
sorry, yes. So
for the listeners, what exactly is deuterium, and why is it different from the hydrogen that you mentioned is also in these molecules?
Sure. So hydrogen is a proton and an electron spinning around that proton, or at least to some degree of approximation. Everything is approximate in the quantum world. Deuterium is different. It actually has a neutron inside of its nucleus, right next to its proton. So an electron is spinning around a neutron and a proton. That makes neutron and proton are about the same weight, roughly unity in relative measurements. So if hydrogen has a molecular weight of 1, deuterium has a molecular weight of 2. So this mass shift, which makes deuterium twice as heavy as hydrogen. In practical terms, if we had deuterium atoms instead of hydrogen atoms on key places or key sites on the molecule where hydrogen abstraction is taking place, then it would be
Now,
taking more.
just so so
Sorry.
essentially what you're saying is uh, deuterium is twice as heavy as hydrogen, and much like a pendulum swinging back and forth,
Mhm.
twice the weight means it's going to swing
Yes,
more slowly.
yes,
And
yes.
and that will also affect the chemical reactions that it's involved in. They proceed more slowly or perhaps not at all.
Correct. And
Okay.
probably a better fitting analogy is a spring. So if two things
Oh,
are oscillating on a spring, in fact, there is a spring component in the quantum mechanical description of a chemical bond. So heavier things at the ends of the spring would be oscillating slower, and that
right.
actually translates into the strength of a chemical bond. So it's more difficult to cut it. Yes. Let me add a footnote. There is a even a heavier version of hydrogen, which has one proton but two neutrons. It's called tritium. But sadly, that just turns out to be too many neutrons, and they make the molecule unstable. It's radioactive.
Right.
So we cannot use tritium for any life science applications because it's radioactive. It will be falling apart and it will be poisoning us in the process. But deuterium is
So
perfectly, absolutely stable and totally safe.
right. So tritium won't be promoting aging. It'll
Yeah,
get you an early
yes, yeah,
death.
yeah,
So
accelerating.
now that's so in a earlier podcast with John Speakman, we got into now he's a proponent of and a developer of the doubly labeled water methodology, where
Mhm.
deuterium is used to track uh, metabolism, right? You give deuterated water to an animal and it allows you to track the progress of the deuterium through the body and you can determine, how many calories it's burning. And this topic came up because we had both been involved in a conversation online about how too much deuterium is harmful. And they were suggesting that removing deuterium from lipids would make the lipids, the polyunsaturated fat specifically, less harmful. Now, you mentioned in your book that if you give an animal water with a third deuterated water, that is toxic to the animal. Is there any effect? And Speakman's point was that the amount of deuterium in the environment is so tiny that it'd be basically, unless you took a super enriched quantity of deuterium in your food or whatever, that it'd be impossible to get to a toxic level. Can you talk a little bit about the toxicity of deuterium or potential toxicity of deuterium
Sure,
and
sure. Yes, it's a very, very important point. Thank you for raising it. So basically, catalytic pockets of enzymes operate by having lots of reactive groups, carboxy groups, amino groups, phosphates, whatever, which can accept or donate hydrogen. So it's all based to a very large degree on protonation, deprotonation. And we are talking about mobile hydrogens here, when proton is free to leave or free to attach itself. So this protonation, deprotonation drives lots of chemical enzymatic processes. If we have the whole catalytic pocket submerged in D2O, then instead of these exchangeable hydrogens, protons, all these groups will end up having deuteriums. So all the isotope effects will kick in. The kinetic isotope effect, the solvent isotope effect, the secondary, the whole lot. And they will actually result in a total breakdown of this fine-tuned mechanics of the enzymatic catalysis of the great majority of biochemical reactions.
Right.
One important thing which I forgot to mention when talking about hydrogen abstraction, by the way, the abstraction, when the abstraction happens by reactive oxygen species, it's not a proton, not H plus, which leaves. It's an H with a dot. It's a hydrogen still retaining its own electron. So it's not a proton, it's a hydrogen. Right. So an important difference between enzymatic catalysis and the places to be reinforced with deuterium can be probably described in the following way. I am only ever concerned with non-exchangeable hydrogens. So if there are exchangeable hydrogens, like you have a hydrogen on a carboxy group or an amino group, you add some solvent and they start dissociating and then reattaching themselves again. Non-exchangeable hydrogens are sitting there for good. They're covalently attached and they cannot be broken or released unless there is reactive oxygen species attacking or something like that. So there is a principal difference. So that's my first point with regards to the toxicity of D2O. These
so
deuterium...
essentially what that boils down to then is that it can slow the reactions down to a point where the organism's unable to function.
I would say it doesn't slow them down to the point where they're unable to function. Rather, I would phrase it this way: everything goes haywire once you change that. It's like totally goes every which way, not the way it was optimized by evolution, but haphazard, kind of random way. But the places on molecules which get damaged by reactive oxygen species, first of all, they are all the same, always the same places. It's not just any place on an amino acid or on a DNA base or on a lipid molecule. There are always unique and specific sites within molecules which get attacked by reactive oxygen species. For example, in fatty acids, it's only polyunsaturated fatty acids, the ones with more than one double bond, which gets attacked by reactive oxygen species. And it's always between the double bonds. It's a double bond, CH2 group, a double bond. So it's always only at the CH2 groups between the double bonds that the attack happens. And if only these positions are deuterated and nothing else, we are minimizing the chance that there could be a release of deuteriums into the organism. At the same time, we're reinforcing just the right places. But just to give you a peace of mind with this, but I did these calculations multiple times, and they are mentioned in the book as well, and they're published. So if the amount of polyunsaturated fatty acids which we need to be taking up daily to build up their presence in the membranes, hopefully we'll come to this a bit later.
These are the deuterated
polyunsaturated fatty acids.
The PUFA.
The amount of these materials is such that if by some magic, which doesn't exist, we were to release, if we would build up the 20% presence in all membranes, among all the polyunsaturated fatty acids, 20% will be our materials. That will be enough to shut down the chain reaction in the whole of the membrane. But if by some magic you would take this 20% throughout the body, the brain, the eye, from everywhere, the muscle tissue, and release the deuteriums from them in one step instantly, the quantity of D2O that you could produce from releasing those materials will be orders of magnitude below the toxic level.
Okay.
even if that method
D2O
exists.
is deuterated water.
DTO is deuterated water, but
Right.
if
Okay.
when you release deuteriums from, say, an OH radical attacks a molecule and grabs hold of a hydrogen atom, not a proton, hydrogen dot, it OH dot and hydrogen dot recombine, giving you water. So
Right.
if the same thing happens with radicals and deuterate materials, you'll end up having deuterate water. So if it were released by some non-existent pathways in one go, you will still, per body weight, you will be orders of magnitude, like 4 or 5 orders of magnitude, below the possible toxic level of DTO. So we're perfectly safe. But that method does not exist. And these
Okay.
things stay because they're more stable. Yeah.
Okay. And you've done, I mean, we should point out that you've done a number of animal experiments in this line of research. And
Yeah.
I'm presuming that I haven't read all of your papers, but I'm presuming that you haven't seen any toxic effects from these lipids,
Yes,
deuterated
there was no
lipids.
toxic. It's either in some models which turned out to have, or diseases, if you will, which have an element of lipid peroxidation. There are great many such diseases. Then we have a positive effect. But there are also models in which lipid peroxidation is just irrelevant. In that case, deuterated lipids behave identical to non-deuterated lipids, not giving any biological effect at all. So it's either nothing or positive effect. I know it may sound too good to be true, but that's there
Well,
are probably
we'll get into the experimental
yes,
work
yes, yeah,
in a little bit. Okay, so that's so yeah, I mean I've before, in the previous podcast with Professor Speakman without realizing it, I was referencing your work in commenting on how it appeared that adding deuterium to PUFA made them safer, not more dangerous. And he also looked into this because, he runs the deuterated water database and has done a lot of experiments also with deuterated water in animals and humans. And he's never seen any negative effects on either metabolism or the entire organism in the course of doing these experiments. So we pretty much concluded that the risk of low levels of deuterium causing a negative effect is essentially non-existent. Um, but with the caveat that the dose makes the poison, and if you know, start chugging deuterated water for the next 10 years, you might manage to give yourself deuterium poisoning. But folks at home, don't do that. Assuming you
but
can
you
even
will you
get
will
the
need you
stuff.
will need to take in a lot of DTO to get to that point. It's 30%. We have for per 70 kilogram adult, there are probably about 40 kilograms of water. So
Right,
one third of that has to be deuterated to expect some bad effects, and that would be like 15 liters. So you have to
right.
have 15 liters of DTO in your system. That's
Okay.
challenging to get there.
And expensive.
And very expensive. So it's kind of a stupid way of terminating one's life should one decide to. That's going to be very,
Too,
very painful
too.
to get to that point. Yeah.
Okay, fine. All right. So we can put that topic behind us, I think. Um, so now you mentioned Aubrey de Grey, how he got you interested in the lipid aspect of that. Can you describe that a little bit? Because I mean, you have a wonderful segment in your book right at the beginning talking about how uh, lipid researchers are the sort of the Cinderella of the biochemistry world, that everybody wants to study DNA or protons and nobody wants to talk about lipids. And I've certainly, prior to reading your book, I've noticed that. I've noticed so many papers where they mention fats as if it's this monolithic thing without recognizing that there are differences in the biochemistry of different fats. Usually they'll say a high fat diet, assuming that explains everything without looking into the difference. They pay no attention to the fat component of the diet while blaming it for all the world's evils often. So talk a little bit about how you got interested in how your conversations with Aubrey de Grey led you into this area.
Right. So, well, yeah, I was one of the, I guess I was on the other side myself to begin with, because like I said, my PhD was in DNA chemistry. And then I was working for many years in Oxford on different types of DNA-based devices, gradually migrating into the adjacent area of combining DNA with proteins in all sorts of permutations. And so that naturally led me to proteomics, if you will, or chemistry of proteins. And I was aware of lipids, but it was Aubrey who actually raised my awareness of the fact that I should not be really just looking at amino acids and DNA. There are other interesting targets that could be worth looking at, and he was absolutely right. And after that, enough to say, I am not even focusing. When I'm saying I, just stand corrected. When I say I never had any funds to develop anything, grants. It was totally not a single grant application was successful. So I'm really blessed with having access to about 100, more than 100 currently worldwide collaborators. So I don't mean individuals, I mean labs
Right.
who likes the technology well enough to be taking compounds from me and putting them in their models and analyzing what happens. And if the results are good, I also happen to be to end up on the papers and stuff. So these guys mostly currently work on the lipid aspects of this. For some technical reasons, which we may want to maybe zoom in a little later, it has to do with the fact that all the damage arising from reactive oxygen species attacking, say, DNA bases or amino acids, it is stoichiometric one-on-one. However important the target, you just get one hit, one damage, and that's it. And that ends at that point.
Right.
Whereas with lipids, it's exponential. It's like nuclear explosion, basically. It's a chain reaction. So the
Right.
name of the book is actually like a play of words. It's chains of aging, but what is meant there between reading between the lines is actually the chain reaction of lipid
Yeah,
peroxidation.
your book is very witty and funny and funny in parts. I mean, not to detract from it. I've always thought that being able to inject humor into a serious topic is a sign of intelligence, and your book is definitely a very intelligent and amusing.
Thank you. I'm sure I've grossly overdone it, and it
Oh
will
no,
be.
I thought it was excellent. I was chuckling the whole way
Thank you.
through.
Thank you. So Aubrey just pointed his finger and said, and like this, and he said, lipids. Don't you forget about lipids. So, and that was. It's not that I'm now totally abandoning amino acids and stuff, but the fact that because it's a chain reaction, the effect, the isotope effect, gets amplified along the chain, kind of remotely resembling PCR, if you know what I mean. So it's really
Right,
exponential. So the effect, it builds up such that by only having a relatively small fraction of deuterated polyunsaturated fatty acids, I'll be referring to them as PUFAs. By having like 20-30% of these deuterated PUFAs in the membrane, we shut down the chain reaction, the whole of the membrane, because the exponential nature of the effect builds up the strength of the effect. And
right.
it's not at all like that with amino acids or with DNA bases. However interesting the observations, some of them are, frankly, I am an interested party, but they're frankly stunning. What we observed with amino acids in some models or with DNA bases, but uh, deuterating polyunsaturated fatty acids in terms of the sheer effect beats all the competition hands down. It's just so much stronger.
Okay, so let's talk about then lipid peroxidation, which I'm very guilty of often saying, discussing PUFAs being oxidized, being bad. That's not strictly correct. I'm using a, a common description. I mean, there's the way I explain it when I'm trying to be a little more careful about it is oxidation of PUFAs is essentially referring to using PUFA for fuel, right? Burning the molecule in the mitochondria. Peroxidation leads to the toxic process, the chain reaction that you're talking about. Can you clarify that a bit?
This is a Pandora box, be warned. I can be clarifying it till tomorrow morning. But in a nutshell, PUFAs. Again, I'll be making black and white statements. Of course, everything is 50 shades of gray in between. But just for the
Yep.
sake of finishing this exercise in a reasonable time, maybe in under 4 hours, I'm forced. I'm forced to be oversimplifying things. So one such oversimplification. No, the assumption that PUFAs are burned for energy is wrong. PUFAs are such a precious resource, particularly the long, like omega-3s, but even arachidonic. These guys do not get burned down for energy.
Okay, but
They are
those are
used.
long chain
Yeah,
PUFAs.
the long chains. Yes. And let me give you. You mentioned mitochondria, so let me
Because
give
little
you.
just
Sorry, go ahead.
just to drill down on that point, because the short chain PUFAs, linoleic acid and alpha linolenic acid, do get burned for fuel in excess, was my
If you,
understanding.
yes, it's nowadays, and I know this is your topic that interests you greatly. Nowadays, with the food chains being grossly overloaded with short chain PUFAs like linoleic, it is the case.
Okay.
But the most interesting guys are the long ones.
Right.
So
Yep.
I'd be kind of I'd be mentioning short ones, but I'd be mostly trying to push the conversation towards the longer ones because the brain is 50 roughly, again,
Yep.
roughly rounding it up, it's 50% arachidonic, 50% DHA. The eye, as far as polyunsaturated fatty acids, of course, there are saturates, there is
Right.
cholesterol, there is oleic acid, which has one double bond. But talking about PUFAs, it's mostly these two. In the eye, it's mostly just pure DHA. There is nothing else. And it's kind of throughout the body in other important compartments. Skin, for whatever divine reason, skin has a lot of linoleic and a little bit of arachidonic, hardly any omega-3s. So there are like horses for courses, but the long ones really rule. And for cognition, for vision, for all important things, neuronal systems throughout the body, it's really the long ones. So
Right. Okay.
the long ones are not consumed to be burned for energy. In fact, there is a stunning fact, and it goes as follows. For polyunsaturated fatty acids to get into mitochondria, to be burned through the beta oxidation pathway, and because they come into mitochondria from the outside, okay, so they have to be prepared, they have to be like a viral vector, if you will, right? So they have to be equipped with they are turned into esters with they form esters, these polyunsaturated acids, fatty acids, with a special molecule called creatine.
Yep.
So they form these esters, and it's in this form of these esters that they penetrate through the mitochondrial membranes, get to the other side, and that get into the beta oxidation cycle. So
Yep.
believe it or not, now in the third millennium we are living and working actively, the compound, which would be a derivative, a creatine derivative of DHA, this compound has not been discovered. It does not, well, maybe they missed it. Maybe it exists at a super disappearingly low levels. But in other words, there was no vehicle discovered as of yet which would see to it that DHA gets into mitochondria to be burned by beta oxidation. Because
Interesting.
these compounds are all individually prepared, like there is this derivative of linoleic acid, arachidonic acid, you name it, but not for DHA. So
Interesting.
that must mean something, right? It's really such a precious resource. Well, you had the superstars on your show, Tony Hulbert, you had Tom Brenner. These guys must have told you that it's
Tom
such
Brenna,
a.
who I should mention was kind enough to introduce us. Thank you to
Thank you, Tom.
Tom for
Absolutely,
that.
absolutely, yeah. So, believe it or not, in places where there is simply not much in the way of omega-3s, like in Himalayas, for example. Yes, you can say that the yaks are eating green and blah, 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 and the people, but maybe not everybody is eating yak meat, whatever. Maybe wealthy people do, but poorer people don't. So they mostly feed on grain. And for whatever reason, there is no omega 3s in grain. Omega 3s are in green, omega 6s are in grain. So
Right.
the mother of a child in places where they are not exposed to seafood, she will, and it's not a stereotype, she will be taking her own DHA from her own brain and through her breast milk delivering it to the baby so that the baby's brain will be formed properly, and then not just in utero but also when she breastfeeds. That's what I mean. When the
Right.
baby is not born yet, it will be happening in utero, but once the baby is born, for the first 2-3 years, and that stock of DHA would then last that person. Remember, that place is not blessed with easy access to omega 3s. So that bulk of DHA will last that person throughout the lifespan. It may be not a long lifespan. It would still be considered technically like a deficiency of omega 3 compared to, say, Okinawa or Japanese or whatever. But it will be, the bulk will be there. So every single molecule will be treasured of
Right.
that DHA.
Right.
So
Right.
it's not, of course, they will be burning and getting damaged oxidatively and whatnot, but DHA is a treasure.
It's a precious
Yes,
resource for the
absolutely,
body, right?
absolutely,
Okay.
yeah.
So you go through, so let's talk about um, aging and a little bit, and you discuss, I mean, we're in the middle now. I hate to use the term pandemic because it's been overused of late, but it's appropriate in this case. We're in a pandemic of what are called Western diseases or chronic diseases or diseases of aging, things like diabetes and cancers and heart disease, that incidence of which tends to go up dramatically as you get older. One of the things that we're seeing now is that these diseases are happening more and more to younger and younger people. Um, Talk to us a little bit about lipids and the diseases, whatever you want to call them, chronic diseases or diseases of aging, because I think that's underappreciated. And you do a great, I'll again refer, if Misha gives us the black and white version here, he does a wonderful job in his book of fleshing these topics out. So I highly recommend everybody go take a look at that. It's really interesting as well as a fun read.
Right, right, right. So the book is pretty gray. I'm doing black and white now. As far as the gray stuff, it's all in the book, right?
Yeah. So everybody,
All the 50 shades
if
of
he
it.
says something and it sounds too good to be true, go read the book. He fleshes it out there.
Right, right, right. So, yeah, but the modern world is overwhelmed with what look. I don't want to be kind of invading or encroaching on your turf here. I know how important
No. I want to hear
the
I want to hear your thoughts. This isn't about
right.
me.
Well, I fully agree. There is, I think there is somewhat of a mafia operating, which peddles the interests of big manufacturers. That happened with high fructose corn syrup, which is now probably added to every single food item in the US. And a very similar thing, it's kind of a different industry, but nevertheless, a very similar thing has been happening since the industrial kind of agriculture or industrial manufacturing of food became a norm. That same thing was happening with things called vegetable oils, which I think is a vicious joke to call those things vegetable oils, because what is a vegetable in taking grain and squeezing out oil out of it? What vegetable was actually used for that? Sometimes they, of course, to
Right.
be fair, sometimes they use the word seed oils, but vegetable oils is also used. So this stuff is grossly overwhelmed by linoleic acid, which happens to be a polyunsaturated fatty acid, the shortest one with two double bonds, which is a precursor to arachidonic acid. And arachidonic acid is a precursor to inflammatory cascades. So there could be a little bit of that element responsible for all bad things. People with the maladies that you mentioned, probably fair thing to say, all of them have a pretty strong background inflammation kind of smoldering through their bodies.
Hmm.
And inflammation, at least many some key aspects of inflammation actually start with arachidonic acid, because if you'll excuse this black and white depiction, there is a knock on a cellular door, and a cell looks into the hole, and there is a calcium or glutamate or cytokine or choline or whatever it is that might be knocking on the door, and in response to that, a very interesting mechanism kicks in, a lipase. There are many different ones. So one of them lands on
And
the inner,
a lipase, we should clarify, is a enzyme that
which
processes
releases
lipids in
fatty
some way.
acids from phospholipids. Yes,
Right,
yeah.
right,
So it then releases an arachidonic acid molecule in response to this very first inflammatory signal, pro-inflammatory signal. Another arachidonic acid molecule, which itself is derived from linoleic acid, which overwhelms Western diets. That arachidonic acid molecule is then converted, depending on what exact signal knocked on the cellular door, what exact cell it was, what time of the day, all these things. Depending on that, a combination of cyclooxygenases and lipoxygenases, and maybe even some cytochromes, will take that released arachidonic acid and convert it into a numerous group of compounds called eicosanoids, which are mostly, not all of them, but most of them are pro-inflammatory. Some of them will be doing their pro-inflammatory job inside of that cell. Some of them will reach out, leak out of that cell nearby or further away, triggering further signals. So it's like goes in cascades, like
right.
apoptosis. So it's every next cascade is stronger than the previous one. And the key to that is this humble arachidonic acid derived from linoleic. But that is the inflammatory aspect. But structurally, linoleic acid sits in membranes, and membranes, because in lots of places, like in mitochondria, for example, where oxygen is normally utilized to burn fuel, so there is a normal leak of reactive oxygen species. Some people estimate that up to 1 to 3% of all the oxygen we inhale does not work properly in the OX-phos pathways generating ATP, but it leaks out because nothing is perfect. I mean, if
Right.
your enzymatic pathway is 99.9% reliable, then there is 0.01% of errors, and they accumulate. Think about how many mitochondria, how many times per day. So 1 to 3% of all the oxygen leaks out in form of reactive oxygen species, and that happens inside of membranes, and membranes are made of PUFAs.
And
So
PUFAs
it's
don't
like
like
really sitting
PUFAs
on a
don't like,
gunpowder barrel, having
yeah,
a cigarette or something, and immediately this lipid peroxidation kicks in and starts in the exponential way, not in stoichiometric way, in the exponential way, propagating sideways laterally. And it's not just damaging the membrane so they become more frigid or less fluid or whatever. That all is the case, but then it doesn't stop there. They continue falling apart, forming the whole smorgasbord of really toxic nasties, reactive carbonyls. Carbonyls are things having a carbonyl group, which is like an aldehyde, for example.
right,
But they are even more activated than just an aldehyde because of the chemical structure. These are very, very highly reactive aldehydes. They're not just simple aldehydes. And these things then leave the membrane, and they can stay in hydrophobic environment, or they can go into aqueous to the outside, and they cross-link stuff irreversibly. There is no biochemistry like trypsin and chemitripsin can chop down proteins in the stomach at the peptide bonds, forming smaller fragments or amino acids. But these the bonds which are formed by conjugating any reactive groups with these aldehydes, they are not amenable to proper cleavage by enzymes. Maybe lysosomes and peroxisomes can somehow try to do the job, but never perfectly they do it. And that
right,
stuff accumulates like plasticine, goes bigger, and that's aging.
right,
This is chemical aspect of chemical basis of aging. I'm not saying this is the only element,
But it's
but
a
boy, is it
significant
an
one.
important one and totally overlooked. Let me give you an example of I don't know, a pair of genes. So you have, again, we have to, this is a chemical approach. So we have to be looking not at like top regulators like, I don't know, a target of rapamycin or something. We are looking down at at the soldiers of the process, which are performing the elementary actions. So if you look at the pair of genes, and so there is this heavy cotton fabric, denim, whatever it's called, where you have threads kind of interwoven. So I think there are two types. They have special names for that one manufacturing. I think there is a type of a thread called warp and type of a thread called weft.
Weave, the warp and the weave.
Weft,
Yeah,
yes,
or weft,
yes.
yeah.
So of course, by reinforce, and they gradually wear out. So you get holes if you wear your jeans for too long and stuff like that. So really, to make the pair of jeans really strong, you really have to make them of tarpaulin, or better yet, of some metal foil or something. Then they will be long-lasting jeans. But short of that, if you were just to take this Swift thing or warp thing and exchange it for something much more durable than it was originally, you will not totally make these genes impervious to aging process, but you will surely reinforce an important element, allowing them to last for much longer. Or another
I mean,
kind
what
of,
people don't understand is that, they hear mutations cause cancer. They don't understand that mutations are happening continuously in the body.
oh
And I
yeah,
mean, this
oh yeah,
is a point you make I think you made in your book, that different mutations are happening in different cells all throughout the body. Your body has repair processes. But again, as you pointed out, none of this stuff is perfect and damage accumulates over time.
yes. And let me give you another example from the world of art, if I may. Imagine you have a painting by, say, Dutch masters, 400 or 500-year-old piece. And imagine there is, I don't know, vermilion type dye, which is a bright scarlet kind of thing that actually has mercury in its, or maybe there is this ground up lapis lazuli pigment, which is beautifully blue. So if you are, and there are many other pigments and many other elements in that painting, and it only makes a proper painting as long as each pigment is as bright as it was on the artist's palette. So now one of them starts deteriorating, and then all of a sudden the whole thing changes. It's no longer that painting. You can still recognize some bits, some structures and whatnot, but it's no longer that famous painting. So just reinforcing that particular element would be very important.
Right.
What I'm trying to say, I'm not arguing this is not like either or. I'm not saying this particular approach should be a panacea and the only way through, like a pill which will sort it out. No, it's a multifaceted thing. Everything deteriorates. Every part of the complex mechanism deteriorates in its own way. Lots of fixes need to be done and put in place. I'm just arguing that this lipid peroxidation, much overlooked process, is a very important component of that. And
Right.
fixing that would really make a lot of difference, and it will be really decisive for some particular types of diseases, for neurological diseases, for retinal diseases, for example, just because the lipid peroxidation is such an important element of those diseases. But even in places where it's not like the number one reason for all the trouble, even there it will be helpful.
Right. Okay. Okay. So, lipid peroxidation is involved in aging because it's a source of damage and it's a source of irreversible damage, and it's
Mhm.
building up over time. I mean, in the book, you extrapolate a little bit more on your painting analogy, noting that what a painter uses to bind all those pigments is oils, seed
Yes.
oils,
Mhm.
right? What are known as drying oils, because I mean, that's linseed oil is what's sold in the supermarket is flaxseed oil. It's the same thing.
Yeah.
And you know, I like to use the example of painting. You know, if you finish a piece of furniture with linseed oil, I was taught this when I was growing up, and there's some fun videos of you on YouTube of this happening. If you finish, you know, you're supposed to rub on the linseed oil with a cloth. And then at the end, they're very careful about how you dispose of the cloth because the linseed oil, which has three double bonds, correct?
Mhm.
Is so susceptible to oxidative damage that it will actually burst into flames if you leave it out in the sun. And people have had their houses burned down because they leave, you know, a rag soaked in linseed oil in the window. Poof, into flames it goes. Um, and so that process, what, you know, happening in that rag is going on to some extent, obviously not quite so dramatically in your body continuously. And we have now let's talk about so can't let's talk about antioxidants a little bit because you have in your book the best explanation I've ever heard of why antioxidants can't protect our membranes. Can't we just take vitamin E and won't this whole problem go away? I mean, that's what, you know, that- that's kind of what the implication is that, oh, you don't need to worry about, you know, lipid peroxidation. Seed oils come with vitamin E and you eat that and it protects you. And, you know, never mind the worries about seed oils oxidizing. It's all okay. Just take your vitamin E along with it. Discuss that.
Um, Again, that distills down to the same difference which we discussed, comparing, I mean, say, oxidative damage to amino acids versus oxidative damage to polyunsaturated fatty acids. One is a stoichiometric process. Again, stoichiometric in chemistry just simply means one to one.
So it's a
One
linear
step,
process.
one to not just linear, but just one to one.
Okay.
One molecule reacts with another molecule, out comes a product. This is it. The process is over. There is no
Okay.
continuation. Okay. Uh, and the chain reaction, just what it says on the tin, it just continues. And the worst part of the chain reaction can be linear from this to this to this, but unfortunately, it's branched in case of lipids. It can go at any point. It can go branching. So it's really like a nuclear explosion. You can control a nuclear power station or nuclear bomb. Before it detonates, you can control it. You can keep the plutonium parts apart enough, or you have graphite things dipped into the fuel. You can control it. But once you make a mistake and it goes off, there is no bloody way you can control it from that
Right.
point onwards until it totally does what it wants to do, and then it stops because it runs out of fuel. It's the same thing. So antioxidants operate in a stoichiometric way, not in the chain reaction way. So the chain reaction, which goes branching every which way, one little branch, if it bumps into the right antioxidant in the right place, it will stop. But you cannot stop all branches, and it gets worse because by you see the membrane, it's a very fine mechanism. Some people say that when life was appearing way before RNA, DNA, this RNA world, whatever, it was actually membranes that formed at the black smokers 3 miles down, and they were the compartmentalization was the first thing, and then differences across membranes, like gradients across membranes of all sorts of things, was the second thing, and then all other chemistries started coming in, including the people's beloved RNA and whatnot. But this is not my hypothesis. Don't shoot the messenger, right? That's just what I'm reading about. So the membrane is only a membrane playing its vital roles, and there are many. When the fatty acids are arranged like that, the reason I'm using two sets of fingers is because this here is a hydrophilic part. This is facing aqueous. This is facing aqueous, and in between there are two leaflets of the membrane kind of in contact. This is all hydrophobic here, okay? So there are only, this arrangement is what's needed for the membrane. Now, let me show you something. So if you have, this is an antioxidant. No, that still looks like a finger. That's a bad example. Here, this is actually does look like vitamin E, like tocopherol. Very
There
good.
we go.
So
Excellent.
you can put it in the membrane like this, But you see, it disturbs the membrane. It's not really a proper membrane right here. It will, if the lipid peroxidation reaction gets initiated here, if a reactive oxygen species is injected into the membrane at this step, and this it turns into a radical, this tocopherol will intercept it and the chain reaction will stop. But what is the chance of that? There is only
to go back to your nuclear analogy, it's like a cooling rod.
Yeah, like these graphite things, yes. But you cannot have, there is only that many molecules of antioxidants, like let's say tocopherol, vitamin E. The normal ratio for a normal membrane is 1 tocopherol per 2,000 fatty acid, polyunsaturated fatty acid residues. Because if you had more, you would have disturbed the membrane, and it will not be sustaining the chain reaction, but it will no longer be a membrane.
Right.
The membrane is only a membrane when it's like this. You start adding antioxidants, they start spreading their legs apart like this, and that's no longer a membrane. So that's why there is only a very limited pool that can be delivered, and you can be eating tocopherols by a bucketful. But because of these sophisticated transportation systems throughout the body, not an additional molecule will get into your membranes. It will be just coming right through, and nothing will actually be used or put into membranes along the way. They will, because the systems that transport it, they know exactly how much is needed, and that is like 1 tocopherol per 2,000 residues, and they will maintain that ratio. They will not exceed. Okay.
And you also mentioned that it's even worse than that, because if you're eating your bucketfuls of vitamin E, it can actually be a pro-oxidant in some circumstances.
Right. But we're not. I'm not. We are talking in black and white terms. That would be great.
Well, but that's I mean, that's a very, I can't tell you how many people I still encounter who say, "Oh, you just need to take vitamin E," and I say, "Look, they've done the RCTs in humans showing that vitamin E is harmful." In excess, and it's not, you can't, it doesn't work to stop the chain reaction the way people would like it to.
To be fair, though, the guy who discovered it about 35 years ago, Roland Stocker, his name is,
discovered what?
Totally discovered the fact that tocopherol can be a pro-oxidant.
Okay.
The guy's name is Roland Stocker. He is a Swiss, but then he spent all of his career essentially in Australia. He actually discovered it in a case which had nothing to do with membranes, because that's what tocopherol does in LDL particles. And LDL particles have no membrane structure. They're just little balls, like call them lipid spheres or lipid balls or something. There is no membrane structurality.
It's a protein.
Well, but there is a lot of lipid also. So it's lipid protein particles with some tocopherol. So tocopherol does that bad thing only in the format of these things. I am not aware of tocopherol being pro-oxidant inside of the membranes.
Okay.
It is a pro-oxidant with regards to these cardiovascular conditions, blood lipids and stuff like that. Having said that, you cannot exceed this 2,000 to 1 ratio. And no attempts, but other antioxidants like artificial, well, there is also coenzyme Q, which some people argue can stop the chain. There are some thyroid hormones. That's anyway. Many molecules are claimed to be able to stop the chain, but this limitation is still there. You cannot have enough in the membrane to stop the chain. It will always be going along the chain reaction, no matter how many antioxidants you take, because of the structural limitations of the membrane.
I mean, we should note that in the body, there are a variety of different antioxidant systems. I mean, it's a layered defense, and the goal is to control, it's, in the embryo, in the developing organism, it actually uses waves of lipid peroxidation to remodel the organism, right? If it says, oh, you need a heart here, you'll get a wave of lipid peroxidation, this chain reaction, to carve out that part of the organism so that there's room for a heart to develop. And then it uses glutathione to stop the chain reaction, right, to contain it in the area in which it's needed. So, I mean, these are all fundamental processes. It's just, we're talking about when they start getting out of control that
And you can also, in those cases, you can also control it not by just giving or taking away antioxidants. You can also control these processes by giving or not giving appropriate PUFAs to
right,
that particular organ so that there
right,
is fuel to be burned or there is no fuel to be burned. But sadly, there is no such choice for our brain, for our eye, for our most important, like heart or blood vessels. They have to be made of that particular ratio of polyunsaturated fatty acids, and there is no compromises. So that's the structural requirement for these organs. So unfortunately, we are in a way doomed to lipid peroxidation because it's unavoidable.
right, right. We can just try and make it less likely to happen, essentially, is what we're doing, or try and come up with
Yeah,
strategies that stops it
yeah,
from
yeah,
getting out
yeah,
of
yeah.
control. Now, one other thing I learned from your book that I'd never heard before, you talk about, so one of the interesting attributes of membranes in aging is that they tend to accumulate DHA in humans. You see this in the heart. You may see this in other organs, but I know specifically this happens in the heart. Now, you mention a Japanese scientist who found one would think, who found a paradox or an inversion where we know that PUFAs, the more double bonds in the PUFA, the more susceptible they become to lipid peroxidation. But this doesn't seem to happen in membranes, that there seems to be an almost inverse relationship. Could you talk about
Mhm.
that a little bit?
Yes, although that will be necessarily fairly technical, this particular question. But yeah, so it's called a Miyashita. Well, paradox is a word I used, but he has a bunch of papers where he repeatedly for decades was saying, look, guys, I know the mantra. I know that the kind of the known kind of parameters describing oxidizability of PUFAs go as follows. Linoleic acid with one CH2 group between two double bonds has an oxidation kind of ability of one.
Right,
Linolenic acid with three double bonds and therefore with two positions between them has double that. Arachidonic acid with four double bonds and therefore with three positions has roughly triple that, etc., etc.
right,
But that is what people are observing doing kinetic studies in solutions with no membrane structure. So they take some polyunsaturated fatty acids, dissolve them in, I don't know, benzene, add some oxidant, bubble oxygen through it, and measure using some chemical techniques the disappearance of that oxygen. And the only way for oxygen to go would be to attach itself to these fatty acids. They can kind of assess the reactions using that, and that is done in organic solvents. But when you switch to membranes, that guy is saying that he still publishes, I believe, that the trend is reversed, and actually the longer things are more resistant to oxidation in the format of membranes compared to shorter things. And
which
he was open about that. He said, look, I'm as baffled as you are about that. My experiments are rock solid. It's definitely, I repeated, reproduced, blah, 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 hundreds of times. This is the data. How to explain it, I don't know. And there is a wonderful guy in, sadly, tragically for lipid science. He retired recently, Paul Els, a good friend of Tony Hulbert, by the way, from Wollongong University.
oh,
And
he
he
was
explained,
his co-author in a number of papers.
yeah, exactly. Yes,
Right,
Paul Els. Yes, he explained it. He said, look, it's because you have all every in chemistry, the mantra is that you all the reactions want to reactions prefer to happen within the same molecule rather than across two different molecules because it takes a bumping between two molecules for the reaction to get started. But if it's within the same reaction, this end of the molecule will always find the opposite end of the same molecule much faster than two molecules separated by solvent. Basically,
right,
intermolecular reactions go faster than between two different molecules. And he said, look, DHA, it has like five bisallylic meaning between double bonds. It has five oxidizable positions. So when one of them gets oxidized, if we were talking about linoleic acid, one position is knocked out, and this is it. There is no more nothing that can get oxidized in linoleic acid, so it's forced to go laterally, affecting other molecules. But in DHA, it's different because once you have one of the positions knocked out, now this radical sitting on this position can actually attack intermolecularly within the same molecule. It can attack the next oxidizable position within the same molecule. So it kind of crumbles along, keeps damaging sites within the same molecule, of which there are 5 originally. So it doesn't go laterally. But when people are talking about lipid peroxidation in membranes, they are talking per bulk membrane. They are saying that much of a volume of a membrane got damaged. So for linoleic acid, that was indeed the case. It was going laterally because there was only one position to get damaged in each molecule. So it was going laterally, damaging a chunk of a membrane, whereas DHA was procrastinating because it was busy oxidizing itself all this time.
So now this is just given me an insight in engineering. There's something called a sacrificial anode, right? So if you have a caustic substance inside something subject to oxidation like iron that's prone to rust, they will put an like a plug that is even more susceptible to oxidation than the iron.
A decoy, yeah.
A decoy, right, exactly. And that will, and one of the maintenance things that you have to do in such a system is you periodically have to replace the sacrificial anode.
Yeah.
Because once it's gone, it doesn't work anymore. And it seems to me, what's always confused me is that the brain is the organ most susceptible to oxidative damage, yet it has all of these molecules that on paper seem to be the most likely to oxidize. But if this is the case, you could look at DHA and arachidonic acid as sacrificial anodes that, even though each individual molecule may be more likely to oxidize, that having all of these molecules in a system, they're each acting potentially as a sacrificial anode.
You are, interestingly, you are coming quite close with your musings to the topic, which is kind of abandoned now, but it was popular at some point some years back, where some people were calling PUFAs antioxidants.
Right.
Yeah, that's essentially what you are saying now, and but I think it was that idea was debunked. It's just the role played by DHA and arachidonic in the brain, or by DHA in the retinas. It is so massively, overwhelmingly important, and we only are ever scratching the surface in terms of understanding. So much is still not understood. There are
Right.
so amazing number of totally not understood concepts and things. Like for example, the signal. If you just calculate, so there is this so you have retina and some auxiliary layers of neurons, and then there is a cable made up of retinal ganglion cells, which goes to the back of the brain and delivers the visual information. So if you just calculate the rate at which an intercepted photon by rhodopsin from your retina, when that signal reaches the brain, if you calculate that rate by calculating, okay, this neuron is that long, then there is a synaptic contact. So instead of chemical electricity, it is converted into little mediator molecules which cross the synaptic space. Then the electric signal travels along the next neuron, etc., etc. If you calculate all these times, you will end up with a time which is much longer than it really takes for the signal upon receiving a photon to get to the back of the brain. What the hell is going on? Nobody understands it, but some people blame DHA for these mysteries. What I'm getting at, probably unlikely your theory that DHA is a dumping ground, because the brain wants to preserve DHA at all costs.
Well, I wouldn't say it's a dumping
DHA
ground. It's a way of controlling it and not getting into the chain reaction.
Well, maybe
right?
there is something in it, yes. But
because you're way better off
yeah.
sacrificing a single DHA molecule than having that propagate laterally throughout the membrane, which is essentially what's happening in diseases like age-related macular degeneration.
Yeah. Yeah.
Okay. Well, anyway, that just sprung to
But
mind.
yeah, just to support your sacrificial decoy part of a machine, I think in the shipbuilding and in submarine building, they use a lot of that because some of the metal parts of which are submerged, they
Right.
will be talking to each other through electrochemistry. One will be getting oxidized, another one will be getting reduced. You don't want that, so sometimes they put rods of the appropriate metal or alloy there such that that thing gets dissolved at the and but you are preserving the other elements of the ship. So yeah, this concept is exists everywhere. Yeah, I know what you're
Yeah.
talking.
Well, it's a hard thing about being in this field is you have these brilliant insights and like, oh yeah, they've known that for they've been thinking about that for decades. Nice
No, no,
try,
but not for
Tucker.
DJ, not for DJ. That's a totally new thing.
So anyway, okay, I think that's probably enough background. Let's start talking about your research. I'd like to just mention that at one point you were involved with a company that was looking to uh, use this as a therapy, but now you're associated with the
I'm no, yes,
universities that you're
I'm
working
just
with.
involved with universities now. Yes.
Right, okay. Um, do people get bent out of shape about that? And your history is your history. What So let's talk about some of the experiments that we've done. I mean, we've talked a lot about, mitochondria, and mitochondria are probably the mitochondria and maybe the eye are the two spots in the body that are most susceptible to lipid peroxidation, right? The eye, because of light coming in, will peroxidize these lipids. And obviously, mitochondria is basically a fire in the body, if you want to look at it
Yeah.
that way, that's spewing out a lot of oxygen and also subjecting these lipids to peroxidation. Have you ever looked at the effect of uh, diluting PUFAs with deuterated PUFAs on mitochondrial function and lipid peroxidation in the mitochondria?
Yes, we did, and there are you can study mitochondria in the format of, well, of course, in the format of organisms, but then it will be difficult to interrogate exactly what's happening in mitochondria. So people either use cells and then use some secondary endpoints to assess mitochondrial performance. Or people can use mitochondria as separate preparations. And there are many interesting techniques these days which allow people to look at things. For example, there is a wonderful technology called seahorse machine, which
Hmm.
basically measures oxygen consumption by mitochondria, and through that measurement, it can look at different stages of mitochondrial performance, and kind of it's very informative. So yes, we looked at in all formats. We looked at cells derived from human donors, which were disease carriers, and the conditions they had were known to be mitochondrial diseases. We looked at intact mitochondria from yeast cells or other cells which were not bearing any disease, but we were hitting them with additional stress from the outside, like
Right.
oxidative stress or this or that. And then we will have two types. One of them will be loaded with normal polyunsaturated fatty acids, another one with deuterated ones, and we were comparing which subtype will be resisting the stress better and stuff like that. And PUFAs were always protective and pretty convincingly so. There are several papers to go with this statement, and yeah, PUFAs are good for mitochondria.
So now, is it necessary? How do you replace all the hydrogens in a mitochondria because it's a pre-existing organelle? Excuse me, I presume that you're taking out of you're isolating from a cell. How do you replace all the hydrogens with deuteriums? Or is that
It's
not
not
necessary?
you are not yeah, let me kind of rephrase it slightly. We're not replacing hydrogens with deuteriums. We are replacing normal polyunsaturated fatty acid non-deuterate with deuterated versions. We prepare them separately and then give them. And not just mammals or humans are craving PUFAs. You have any cell and you put it on a
Right.
petri dish and you add PUFAs to the medium, they will start taking them up. And there are some turnover rates which are well known. So if we expose cells for like an overnight or 24 hours to a medium which contains deuterated polyunsaturated fatty acids, cells will start taking them up and end up having enough incorporated for us to see the effect. Because remember, if this is a hull of a membrane, we don't need 100% of PUFAs to be deuterated. We
Ah,
only
that's
need
key.
a relatively small fraction. Let's round it up to, I don't know, 30%. So, and that is actually quite doable. It would have been much more challenging if we needed to exchange every single PUFA for deuterate one in the body. It will totally rewrite the dietary habits and will be a long time. But because we only need that relatively low, about 30%, that is actually quite doable for cells, for animals, for mice, for humans. Yeah, and that's how we were delivering the reinforced DPUFAs into cells or mitochondria, and then we were just taking readouts from different readouts from those. Yeah.
Okay, so it works it works to protect against lipid peroxidation in the most obvious place to do it. What other experiments have you done in animal models? I mean, I see you did a paper looking at atherosclerosis. That's obviously a hot topic. It's the number one killer
Yeah.
around the world.
Yeah.
What did you see there?
On some endpoint measurements, that was a special model which had a disturbance in cholesterol. It's called Leiden mouse model of cholesterol, and the well, it's multi-layered. The thing, of course, on the molecular level, to for us to show the target engagement, we will always be looking for lipid peroxidation products, be it lipid peroxides or carbonyls like HNE, HHE, or maybe isoprostanes. All these different groups come from lipid polyunsaturated fatty acid molecules getting oxidized, and then they continue falling apart. So we just we look at different groups and we tick that box. Okay, we see the lipid peroxidation engagement because in mice with on D PUFA diet, we had less of those bad guys than in mice on H PUFA diet. Then, depending on the model, let's say atherosclerosis model, so there are the plaques. I think there are several parameters. I may make a clown of myself. It's really a medical kind of fine medical points, but I understand that there are bifurcation points in the blood vessels. And what is particularly important from the development of atherosclerosis is how close to the bifurcation point the depositions of plaques happen.
Right,
And
right.
on that, the closer the worse, I understand, because presumably because it can clog the not just the flow, but kind of the flow in several directions. So we had on
Right. And
that,
the idea I think is that there's turbulence at those junction points and that
yeah,
the turbulence makes it
also
right.
that, yeah. So the size of the lesions, the geographical position of these lesions within, like how far from that bifurcation point, or how close, on all these parameters, there was some favorable observations in mice, which were fed DPUFAs for several weeks. Oh, actually, that's probably a good place for me to zoom in with a comment because of this. So the approach is not going to work like if you feel pain and you just pop an ibuprofen pill or something and the pain is gone. Unfortunately, it will take some time to build up the necessary level, which in case of mice usually takes from 4 to 8 weeks. That is the amount of time we have to feed animals on H or D PUFAs to then build up enough presence.
Okay,
But maybe if you,
that's a very important point. This is not like I mean, I guess, it's like if you have a heart attack, they'll give you an aspirin because it has an effect on clotting that's thought to be beneficial. This is
yeah,
more like taking a statin, a drug I'm not particularly fond of, but in order to get the benefit of it, you have to be on it continuously because
yeah,
the purported benefit comes from altering the metabolism. So this is similar. You've got to have the protection in place in order to get the benefit from it.
Well, there are
I
certain
mean,
cases. There are certain cases in which I wish we could get the materials in faster. For example, the reperfusion injury
right.
is just begging for the PUFAs to be placed in specific places. However, there is no chance. Reperfusion injury, unless you know it, unless you can time your heart attack or a stroke exactly to the minute, and then start taking deep PUFAs like I don't know 2 months prior, then you are fine. But who can
Well, and
do that?
but you know, if you had an elective surgery, uh, then you could certainly use this, right? I mean, and for the audience, Misha's referring to ischemia reperfusion injury, where you stop oxygen flow to an organ or a part, some part of the body, and then the you know, metabolism stops because there's no oxygen, but some maybe a little paradoxically, when you restart the flow of oxygen, there's a much higher
Yes.
incidence of lipid peroxidation that takes place, right?
Yep.
And so if you're doing a surgery where they've got to stop blood flow to an area and you were able to take, pre-coat that area, pre-populate that area with deuterium, then that could reduce the reperfusion damage, which is often, I mean, in a heart attack, that's pretty much most of the damage is the ischemia stopping blood flow to the heart. And then when blood flow resumes, that's what's causing all the damage, ironically. It's not necessarily the fact that it's stopped, it's that it's restarting. And protecting that would be a huge benefit. So
Yeah.
you
But
couldn't do it with a heart attack, but you could do it with like heart surgery if it was
yes,
not an immediate need for it.
if you can prepare in advance, absolutely. But for heart attacks, for lung conditions which are to do with blockage or with brain, unfortunately, that particular application is probably off the limits for this technology.
Right.
Unless you use it all the time as a supplement, which is a different issue, and then of course you'll be covered. But let me come back to your statin example. Well, I don't think it is perfectly comparable because
Yeah.
it is a negative definitely that we cannot instantly deliver the material in a matter of minutes. It will take long weeks. However, the positive side, the other side of the coin on this is that once you build up this notorious 25-30%, you can then go on holiday, fly away for a couple of weeks, come back, not taking your compounds with you, then come back, and your level, because of the daily turnover and exchange rate, you are perfectly fine. It exchanges to the tune of, I don't know, in humans, maybe I don't know, less than 1% per day or something. So you are back from your trip. A week later, just start on your things. The missing dosing for a week will not make a dent in your level of deuteration in your membranes. It will,
Okay.
but a very small one, insignificant. Yeah.
Okay. Okay. Well, that's an interesting point. Yeah, thank you for
Yeah.
making that. Now you also looked at Alzheimer's,
Mhm.
a mouse model. What was the idea there? Because I thought, we've been told that Alzheimer's is due to this amyloid beta protein building up, and how would DPUFA help in that model?
So again, it's a multi-pronged kind of thinking that went into that. First of all, there are Mark Matson and Alan Butterfield are the two guys who pioneered the observation. I think they went their own ways in the mid 90s, but before that they were both postdocs. I don't remember where, early 90s.
Hmm.
And they were the first to prove, beyond any doubt, that in Alzheimer's, lipid peroxidation and carbonyls are elevated. But most importantly for our conversation, that precedes the plaque formation. That is
Okay.
not the result of the plaque formation. That precedes it. Okay, so that's kind of a godsend piece of data.
Yeah,
Then,
I saw a paper. out of Harvard, I think, demonstrating that injection of HNE into the mouse brain would produce the beta amyloid proteins, as a demonstration that the lipid
Very good.
peroxidation is happening before the
Very
beta
good.
amyloid is being produced.
It's probably even, I mean, what transpired for me from doing all that stuff for almost 20 years now is the fact that, believe it or not, I would actually be reluctant to make special cases for different diseases. To
Okay.
me, it looks like they are converging more and more into one thing, which has the kickstarting process as a as a lipid peroxidation, and then depending on your genetic background, your lifestyle, your this, your that, it diverges into like think about traumatic brain injury, for example. Okay, what
Yeah.
happens is you shake things. There is centrifugal force which momentarily separates the lipids and membranes because of the centrifugal force, right? So stuff starts leaking every which way. Things which are not supposed to be brought into contact are brought into contact. At the same time, there are micro damage to blood, micro capillaries. So blood comes out right into that thing, and there is a lot of iron. So all that melee starts lipid peroxidation. And the very first effect of that is you have this protein called phosphatau, which has to be phosphorylated and dephosphorylated. By the way, it's not just a feature of TBI, it is also present in PSP.
Parkinson's?
In Alzheimer's, tau is implicated across the board. So phosphatau gets covered by the super glue of carbonyls, which are derived from lipid peroxidation products. So it can no longer be dephosphorylated. As
Okay.
the first impact, and there is a splash of these carbonyls, they immediately wrap around covalently, so they cannot unwrap covalently, irreversibly wrap around this phosphatau. It cannot get dephosphorylated anymore, and it tends to form these conglomerates like plasticine, etc., etc. But that is just the original thing that may be happening like 20 years prior. But then look what happens. Some people like football in Europe, soccer players, right, who specialize in headers.
Right, right.
Oftentimes, totally unexplained, they often have ALS. Lots of people have memory losses, dementia, and Alzheimer's. Muhammad Ali, it's called pugilistic dementia or something. He famously had Parkinson's. But look, the initial original effect is always the same. But then, depending on where exactly in the brain, and if you are maybe a smoker or your genetics or what, that unified common denominator then gets percolated into different things, giving rise to different diseases. Do you still want to be talking separately about Alzheimer's or Parkinson's if the origin for them was the same and one lipid peroxidation event? So I
Right.
am actually what I'm weird in this way. Like people specialize and then specialize some more. There is this subtype of Alzheimer's, and there is even a better mouse for that subtype. I am actually going the other way now. I think
Yes.
turn this tap, turn that facet off, nip it in the bud, and there'll be none.
So you're saying, I mean, that's a great point, that looking at this as a disease specific therapy is kind of missing the point. A, you can't really target just the brain with something that's you're taking orally. I presume deep PUFA supplements are consumed orally. Um, but it's going to affect the whole body and affect all of these processes. And I mean, I completely agree with that view. I always point out to people that, all of these aging diseases are all correlated, some of them really highly correlated, which indicates that they're all, it's the same cause. And the different presentations are based on other factors, right? Are you a smoker? Do you have, maybe we'll get into the ALDH mutation a little bit. And, that's going to determine which part of it, which presentation you see.
By
But
the way, Tucker, can I squeeze in something funny
yes,
just to keep you entertained? Since you are not sponsored here by the government and there is no third United States surgeon issuing warnings, Just for your information, smoking is protective against Parkinson's. So
Ah,
if you were born if you picked your parents wisely enough to get you all the anti-cancer genes and you're kind of protected against lung cancer and stuff like that, it's actually advisable. You may want to cut it out from your video
no, no,
video
no.
blog,
That's, I mean, that's a
but
really interesting
smoking is
point
protective
because
against Parkinson's.
there's um, it's also protective against ulcerative colitis, one of the irritable bowel diseases. I think it's ulcerative colitis. And physicians have actually prescribed smoking to people because it completely kills the symptoms, right? When I looked into that years ago, what I found was that they think it's not the nicotine, it's not the lipid peroxides, it's some of the other, there are thousands of
I've
chemicals.
heard maybe with regards Parkinson's, I've heard that nicotine somehow gets into the dopamine, which is a major disturbance in Parkinsonism, substantia
Right,
nigra. It gets into the dopamine pathways and does something there. I cannot say I understand
right,
it, but
right, right. But yeah, it's just don't smoke, folks. I
yeah, yeah,
mean, I
yeah, yeah.
guess if you already have Parkinson's, you should talk to your
Yes, yes,
doctor.
yes, yes, yes. But actually, bringing it back to kind of very well-known cliches, this me making a U-turn and going 180 degrees against the mainstream, which is more and more specialized, more and more split up subtypes of diseases, me going the other way, it is similar, isn't it, to the Babel Tower? Because people lost the ability to communicate, and that's
Yes.
how they never ended up building it all the way to heaven, because because of too many languages. Had they had one language, well, maybe that one language is lipid peroxidation.
Yeah, no,
Going
that's
biblical, going biblical.
I totally agree with that, though. I mean, it's
Yeah,
absolutely right. And I mean, one of the things, I've tried to do is point out to people that, it's not, this is a common factor underlying all of these diseases. And that's why potentially, now let's get into um, aging. Back to the Bible.
yeah,
In, in, is it in Genesis where God sets the life expectancy of
120. Yeah, yeah.
people at 120 years, and in all of history?
Having said that, there are also figures mentioned of like 800 years and stuff. But unfortunately, it looks like I cannot pin down the exact reference, but it looks like some historians looked at that. Looks like that back then they were counting months. So when
Okay, well,
someone was like 900 years old, it was actually 900 months.
right. But
Much more.
after that, but the point is when God changes, when he says the lifespan is 120 years, that's after all of that
Right, right.
chronologically in the
Yes, that's
Bible,
a
right?
New Testament. That's right. Yes.
Right.
Yes.
So he adds a new one. And I mean, we don't have to get into that whole thing. That's only interesting because as you note in your book, there's only one person confirmed in history to have lived past 120 years. So
Maybe.
maybe. I mean,
There is controversy about her, yeah, but maybe. But at least she definitely hit 100. Whether she was 120 or not, she was definitely a centenarian.
okay,
That
okay.
is known for, yeah.
Fair point. But we know, but I mean, the problem I have with all these aging, you know, with the idea of enhancing longevity is we obviously know lots of ways to reduce lifespan, right? We don't have enough time to go list them all, and everybody's familiar with that. But we don't really have any that are credibly shown to enhance lifespan. I mean, we discussed in the precursor call to this podcast that most of the mechanisms that are marketed nowadays as anti-aging mechanisms basically depend on calorie restriction, whether it's mTOR or, calorie restriction itself. But this is actually something where potentially by reducing the level of damage, I think you could credibly see it as extending lifespan. Have you been able to do any experiments looking at that aspect of it, right? Like giving mice PUFA for the course of a lifespan, or I mean, my ideal study would be, this was done by Mark Puder looking at the essentiality of short chain lipids. he did 10 generations of mice with no linoleic or alpha linolenic acid, and they were just dandy, right? So I'd like to see a study where you're doing 10 generations of mice with deep PUFA supplementation, prove beyond, prove as well as it'd be possible to prove that they're harmless, and also see what the lifespan is. Have we gotten to the point where we've started looking into that sort of study?
So there was looking back, talking about making the compounds.
Yep.
It was a two-step process. Originally, we could only make linoleic and linolenic
Okay.
deuterated, and we were doing it chemically by total synthesis, which is very time consuming, very expensive, very lengthy, expensive for us to make, never mind commercial product. It was very expensive for us to have those things, and also impurities and whatnot. And then there was a major breakthrough when a good friend of mine cracked it, and these things can now be made catalytically.
Okay.
So you take a preformed, say you take fish oil
Hmm.
in whichever form or shape, right? And then you add a really, really fancy material to it, and water, heavy water is a source of deuterium. And in one step, you just place deuteriums at the right places and nowhere else.
Oh, wow,
So
that's brilliant.
yeah. So it's really makes it all doable and accessible and whatnot. However, of course, aging was, I mean, the fact that that company I used to be with, it was focusing on neurological diseases, but that was kind of a commercial thing. For me, aging was always the driver, okay? And of course, we did
Well, of
try it,
course,
and
I mean, we should just observe that it's, you know, yeah, you got to make money on this at some
yeah.
point. I mean, if it's going to be, if everybody on Earth is going to get this, and we can debate the merits of that, but you've got to produce a lot of it, and at some point, it's got to be producing a profit. So if you can give it to people to treat a disease as a way to fund future research, that's obviously going to be the most likely means to produce a effective research program, right? I think.
Yeah, absolutely. So we did have a small pilot experiment in which we did observe life extension. However,
In what
several
organism?
caveats, several caveats in mice.
Okay.
But it's small. Okay, hold this thought here. I will come back to it from this point to this point exactly, but let me make some additional comments. Unfortunately, not just in cells, but even the workhorses of longevity research, like Drosophila flies and worms, unfortunately, for many technical reasons, they are not just not ideal, but they are totally irrelevant to the mechanisms we are looking at. Because, for example, if we are interested in, say, so for Drosophilas and C. elegans, it doesn't matter if it's omega-3 or omega-6, they can interexchange them
The
themselves.
fat
They
the
have
fat one
the
gene.
machinery.
Yeah.
Yeah. Also, if you feed, say, DHA to flies, they'll chop it down to C18 or C20. They do not use such long things. So
Okay.
what could you possibly even glean out of these experiments if it's so much different? But it gets worse. There are, again, this is 50 shades of gray, as is always the case with aging. But here it is. It looks like, if we're focusing on lipid peroxidation, it looks like mice and humans. Mice do not model anything in humans, because in humans there is a mechanism to try and not put too much long PUFAs into mitochondria. There are special, so far totally not understood mechanisms of how, say, this particular PUFA gets there, but this particular one does not. I mean,
Right.
it's not just gradients and osmotic things. You have less of that, so more migrates. It's not like that. There are mechanisms which
There's
pick, like, for
there's a
example,
selection process going on
take rods and cones, for example. You have in rods and cones,
in the
you
eye.
have the discs which hold rhodopsin, almost pure DHA. But the cellular membrane which holds this thing. And by the way, these cellular membranes for rods and cones are principally different. Rods just hold the discs in the cylinder, surrounded by a new membrane. Cones are the cell membrane is making the indentations of the stacks, so it's like semi isolated. But cones and rods are principally different in that sense. But let's focus on rods. You have in the discs you have 100% DHA, but in the cellular membrane of the rod itself, which at the bottom of the cell gives rise to all these discs, there is much less DHA. And the same applies to mitochondria down there because
Right.
rods have their own mitochondria, stuff like that. What mechanism is responsible for making sure that there is more DHA here and less there is totally unknown, believe it or
Yeah.
not, because nobody cares about lipids, remember, right? People are only ever concerned with information transfer. This is and maybe with ferroptosis as well. These are the two things, right? So
Oh,
the
I
big
just I just I just want to observe ferroptosis is a pet peeve of mine, that term, and you have a wonderful section in your book on
right.
we
Well,
share a
I'm
view
sure
on the
I'm
on the
gonna get a
term
lot of flack. I'm
ferroptosis.
gonna get if ever a single copy of this book is sold to anyone and the word gets out, I'm sure I'm gonna get a lot of flack for that chapter. But that was anyway. So mice and humans. Mice, whatever you give them DHA, you will find that DHA in mitochondria. Not so in humans. So
Okay.
that could be, and mitochondria, of course, keep burning, keep churning through lipids, oxidizing them and whatnot. Mitochondria are not using this DHA like we discussed earlier on. They're not using them for beta oxidation. They're using them structurally, putting them in cardiolipin and stuff like that, but not humans. So maybe this is the main reason why humans live 100 years and mice live 3 years.
Yes,
Or maybe
mice
it makes a major impact on that. So to what
mice
extent
mice
is even mice predictable of anything to do
right. Right,
so you
right,
see,
right, right.
there are so many issues like that. It's a minefield. It's a bloody minefield. This thing.
Right, right, right. Yeah, that's a great point. But I mean, you got to start with something.
Yeah.
And clearly, even though mice may have adapted to a high PUFA consumption with a short lifespan, if we improve their PUFA quality, maybe, plus they're cheap
And
to work
those
with.
must have been the mice which co-evolved, according to Michael Crawford and Stephen Cunnane. They might have been crawling on a beach, picking up things from that first human who had access to seafood
Right,
on the shore, and he was developing his brain, and mice were developing their mitochondria, and then they migrated together to Europe from there, right along the coast. That's probably we can rewrite a kind of human migration here. Yeah.
right. What sorts of human experiments have been done in looking at this so far?
Again,
Obviously, you can't do a longevity experiment. I mean,
yeah. So
is anybody taking PUFA supplements that you're aware of to try and affect longevity?
uh, uh, I have to double check.
Okay, okay. So let's leave that as a question mark. That's fine.
Yeah.
What sort of
So
human experiments have been done?
back in the times of that failed company trying to develop drugs, again, the drug was entirely based on linoleic acid because when we were
Okay,
getting started, it's a lengthy process of discussing with the FDA, getting permissions, making materials to a certain standard, certifying it, and then applying and getting the permission to run the clinical trials. All that was based entirely on D2 linoleic because that was the only one we could make initially. Or that's how we got started. So
right.
all these fancy, long long PUFAs, they were not available back then. So they were not tested essentially in such settings, but they should, I think.
Okay, okay. What would you like to see done next? If somebody gave you $1 billion to do experiments in this area, what do you think is the most important thing that should be done to move this along?
honestly, there are so, let me rewind back to where I was praising the way it panned out, which all stemmed from the fact that I could never raise funds. So I was forced to go with my hand stretched out and offering people small quantities of material to try it in their models. But it turned out to be a total blessing because even if I had $1 billion, I would not have been able to run 100 different models under my supervision. But right
Okay.
now there are 100 top specialists in the world, and it really covers Australia, Chile, New Zealand, Brazil, America, Canada, Europe, Singapore, you name it, everywhere. And people are genuine, and it could be like a genuine specialist in a particular disease, say Parkinson's or whatever, Friedreich's ataxia, I don't know. And those people are better suitable than anyone else to run those experiments. And they are totally excited about trying it in their setting. And so am I. So I think I would not have wished for a different structure going back 20 years ago. I was always grumpy about it, but it turned out
Fair
to
enough.
be it's actually a better arrangement that it could have been had I had money to spend on this. So, and which is a weird and distorted way of praising my collaborators and saying how grateful I am to all of them. It's just wonderful. Every single piece of data, none was produced with my own hands. Every single piece of data which is now available, which was published in papers and blah blah, was produced by these wonderful guys.
Well,
So
but
I could,
that's actually, I mean, in terms of the utility of this approach, that's a wonderful testimony to it because the biggest problem is you see some therapy that's done in one lab and you take it to another lab and it doesn't work. And here you've got 100 labs that are all seeing similar effects
yeah,
in a
yeah,
variety of different conditions, some of
I
which
agree.
are related to aging, some of which I gather are not. Like Friedreich's ataxia, I think is a genetic condition. Am I correct?
Yes. Mhm.
Right. So
Mhm.
that's okay. Let's talk a little just briefly about most aging research. There's a lot of money in that community, in that community. Guys who have a lot of money who are spending, I guess, what's his name? Brian Johnson, who's spending supposedly $2 million a year on therapies. I don't agree with a lot of his approaches, let's just put it that way. But obviously, some folks, and Peter Tia apparently makes a lot of money with a reasonable, I think, approach to aging. I wouldn't take rapamycin myself, but from what I understand, you've read his book. Most of what he's talking about is pretty sensible stuff. Get exercise, eat a good diet, right? I mean, there's but the point I'm getting to is that in the short term, if this comes out, it's likely going to be a very expensive product, right? And it's going to be a rich man's. If somebody takes this and demonstrates that it has extended their life, it's going to be some rich guy who's doing it. Do you think that's fair to say?
Oh, well,
And I don't think there's necessarily a problem like that.
I think the figures you mentioned, like millions to the tune of millions, 10 to the 6 per year, that it's expensive, but not that expensive. But let me
Right.
let me rewind it a little bit. And yes, aging. It's kind of, let's get a little philosophical. What is aging? If someone is, and it's not my thoughts. It's been discussed every which way for the last 10 years. If someone is bedridden and his brain is switched off and he basically lives off machines and they can sustain him in that state for 25 years. So his brain switches off at 75 and he reaches 100. Is he a centenarian? So
Right.
it's more like they say quality of life compression of morbidity, so that you are healthy to 93, and then once you celebrate your 93rd birthday with your grand children and stuff, and then 2 days later you're dead.
Right.
Compression of morbidity, and
Yep.
you are undergoing 25 years of damage similar to that guy over the next 2-3 days. So looking from that perspective, And aging, what is aging? So some people, aging is just a higher increased ability to undergo diseases. You don't get that disease when you're young, but then when you are aged, some people get, I don't know, joint problems. Some people will get cardiovascular, neurological, blah, blah, blah. So
Right, exactly. Well, I mean,
what
COVID
if
COVID killed old people because they're more
Yeah,
susceptible to diseases in general.
immune deficiency, and that, by the way, that particular there is a catchy phrase coined recently, which is inflammaging. And
Yeah,
remember what we discussed at the beginning, deuterated arachidonic acid could be nicely kind of helping on that front. So what if we just for the sake of an argument, if we just stopped being focused on extending lifespan? What if we started focusing on postponing, pushing further into the future all these horrendous diseases? And if it is indeed the case that lipid peroxidation seems, at least for some of them, to be a common denominator, then we stand a chance.
right.
Whatever it will then, maybe people will get so happy about the fact that they are 90 and they have no diseases that they will all start flying helicopters, and they will all, with booze
Die
and
in
cigars
helicopter
and stuff like that,
crashes.
and they all crash, and they never reach 100, and then some other people will say, look, your stuff doesn't work, these guys did not live to 100. I will probably argue with that. So maybe a better thing to focus on would be to really talk about postponing diseases and fixing the equipment, rather than this pretty empty in itself goal of extending lifespan. I'm not like avoiding it. Would be nice. I would love to live to just read. There is this section called back of the envelope.
Yes,
So if you could kindly read the very last paragraph there, on which is total kind of
of
um,
your book.
yeah, there,
Yeah.
that analyzes the situation in which all these things will have been sorted out, and what the hell do we do then? So I think the goal should be quality of life, mitigation of age-related diseases, and so that is as far as which goal to pick. And now back to what other things are in existence and what people are talking about. I think that lots of compounds like rapamycin related stuff, sirtuin related stuff, and the appropriate small molecules like resveratrol and all the rest, metformin, all these guys, even calorie restriction or some calorie restriction mimics. What
Hmm.
happens with this with all this Vigovi and other things? It basically makes you hate food, right? You eat something which makes you totally not hungry. You no longer enjoy food. So in a way, you have all these different things from different facets, but they are attacking the same exact mechanism. They are pushing an organism into some kind of semi-hibernation state when the supply of food is not really there. So you want to overcome it. You want to maybe wait through a bad season and emerge still alive on the other end when the harvest is good again. First of all, these things don't seem to work in primates. Even the two controversial monkey studies, where one of them, I think they reported that their fur was more shiny, but not much in the way of life extension. And another one, they fed them, what they called calorie restriction was normal diet, and the control group was stuffing their faces with like 10 times the number of the quantity of calories. So they naturally died younger because they were totally victims of metabolic diseases. You could not
Well,
draw a conclusion from that calorie restriction was helpful, because there was no calorie restriction. There was just normal diet in the experimental group. Other than
right.
that, it
Well,
doesn't
those
seem to.
those just a little side note about those two studies. You're referring to, I think, the two rhesus group studies that were done in
Yeah.
parallel at two
On
different.
rhesus monkeys, yes.
Right. So one of them they mentioned that
Macaques.
one of the diets they mentioned they got fat. The other one they didn't. On the control non-calorie restricted diet, they
Yeah.
got fat. And those were the ones they were feeding corn oil as their fat source.
Right.
So even in that study, there are some very interesting things that we can take
Right,
away
right.
from
No,
it.
it's very. I will never turn down any study. Every single study, whichever it
Yeah.
is addressing, is worth doing. Absolutely. It's easy for me to say because I never do any studies myself. It's always my
Right.
collaborators, right? But again, back to so these calorie restriction related mechanisms may very well draw a blank in terms of trying to extend human lifespan. But even if they didn't, they are still addressing one same mechanism. Resveratrol kind of controls how sirtuins make sure that DNA is wrapped around tightly, cannot be read out. Therefore, cells go into like sleeping state and repairs kick in because there is no propagation on us. Things like that. What I'm trying to say is that this approach we're discussing here is totally orthogonal to all those things. It's not antioxidants. It's like
Right.
structural. It's not based on calorie restriction or anything. So I think nobody should be taking it as a threat because it's compatible with everything there is. Whichever
Right.
favorite approaches or topics people are testing on themselves, this thing is going to be orthogonal to all of them.
Right.
So, taken separately or taken with, like Brian Johnson, his name is, right? Like he takes
Yeah.
whatever, 30 or 300 different things, it would still be orthogonal to all of those.
Yeah. No, or potentially even, I mean, I've seen I think I saw one study that suggested that part of the mechanism of rapamycin is a increased capability to repair H&E damage. So potentially, you could supercharge that effect by reducing the H&E damage, reducing the aldehyde damage, which is not going to go away, but is going to be lowered a lot. So yeah, no, I think those are great points. Living, I mean, what I always, the problem with longevity is not just the idea that um, you don't want to be, as you said, a vegetable for 25 years and then, yay, I've lived to 100 and I've been miserable for the last 25 years. But we've got lots of organs that just kind of wear out after a while, right? So having something that's going to either repair damage, which doesn't seem particularly feasible, or prevent damage is
Or
key.
at least slow it down.
Yeah, or at least slow it down. Because I mean, our hearts don't regenerate, our brains don't regenerate, our eyes don't regenerate. There are lots of organs that seem to have a built-in lifespan. Uh, and I certainly don't want to be 200 years old with all of those organs in a terrible state of repair. That would be a curse, not a blessing.
Yeah.
Um, okay. Any points that we didn't cover that you want to hit on?
The word favorite would be a wrong word here, but the thing which particularly interests me in all this relationship between lipid peroxidation and how to resist it and how it does damage to the body concerns almost 600 million people who are the unfortunate folks
Yes.
having the aldehyde dehydrogenase mutation. And just a quick reminder, when we imbibe ethanol, it gives us high, but then the body starts getting rid of it, and on a way, it first converts it into an aldehyde, which gives us the headache the morning after the night before. And then that aldehyde is further oxidized into acetic acid, which is totally neutral. It can be used as a building block, or it can be washed out, whatever. So that process stutters at the level of an aldehyde in these 600 million unfortunate folks. It's called Asian flash mutation or something. And that
Asian
is not,
flush.
yes, yes. So it's not just as innocent as that. It's much more sinister and pernicious because these aldehydes accumulate and do a lot of damage. It's not just that they have flushes, that's what aldehydes do, but they do lots of damage which those people don't see. So lots of deadly conditions are elevated in these unfortunate folks. Of course, there are heterozygous and homozygous variants. Homozygous are much stronger hit than heterozygous, but even heterozygous are not feeling particularly well. So it is a huge topic. 600 million people, and PUFAs are very relevant to it. But first of all, you guys
Well,
covered it.
explain how PUFAs are relevant to it. Because yes, we did do an episode. I'll in the show notes or somewhere, I'll put a link to that.
Right. So, but even if people don't drink, the constant smoldering of lipids producing there is a constant production of these aldehydes, which are constantly being formed, and removal of them is very inefficient, particularly in people missing one of the key enzymes.
Right.
So by putting those people on this particular, I don't know, whatever you want to call it, supplement, reinforced lipid, nutraceutical, whatever you want to call it, putting those folks on that thing, totally irrespective of whether or not they drink. Many of them don't because they don't enjoy the process, but some of them still do. Irrespective of that, just reinforcing key parts which cannot possibly be producing nasty compounds because their bodies are much less prepared for that than the bodies of people who don't have that mutation could be very helpful for those folks.
Yeah, that's a great point. Yeah. And I think another, you know, one of the hot new treatments are these PCSK9 inhibitors, treatments for heart disease. And that's based on a human mutation. And, you know, the fact that the mutation exists and has a positive effect on heart disease is held up as the proof of concept for that particular drug. And I think the ALDH 2*2 mutation, the Asian flush mutation, does the same thing here, right? Those people are more susceptible to the diseases of aging than somebody without the mutation. And it demonstrates that this is, and, you know, it demonstrates that this is a real human health problem. It's not just a lab artifact, right? We've got, you know, it's the single most frequent human mutation, I think I've read. 600 million people, 50% of the people in China, 40% of the people in Japan, from my reading. You know, this is a major, with an enormous amount of literature coming out of those two countries looking at this. So this is a wonderful demonstration that of the real health impacts of lipid peroxidation in humans. And that's not even the most important protective pathway.
Yeah.
Um,
and we did. There was a study. So these heterozygous carriers retain variably, depending on the exact mutation, maybe up to 7% of the activity. Homozygous carriers retain around 1, but we tested it in mouse knockouts, which had 0 enzymes. And they are actually talking of common denominators and things being connected to everything, being connected to everything else. Those mice are a known model of Alzheimer's. They
so
lose.
whoa. Wait. So you tested DPUFA in a group of mice that have a
They were
dysfunctional
an
ALDH,
LDH2 knockout. Yeah.
and they're using that as an Alzheimer's model.
Yes.
And what did you see?
And the guy that was done in Canada in the Kingston University in Ontario, the guy was actually a specialist in Alzheimer's. He tested all sorts of different models, and he liked that one because it would guarantee things, and it would be very nicely kind of, there will be no doubt. It's like a clock.
Right.
So, and I can, well, actually, that's interesting question about the results. That was one of the rare cases where the result was essentially digital. Mice on PUFAs did not have any indication of the disease at all. They were a totally normal, healthy phenotype. Just on account of them getting PUFAs for a few weeks, they came across as perfectly normal mice. It's not like they were better off than mutant mice on H-PUFAs. They were absolutely perfectly normal, retaining all the proper endpoints, whichever things we measured. There were like memory tests, the
Right.
water maze, and all sorts of things. So that was one of the. We did have such a amazingly strong effect in other models as well, but that was the first time when the effect was just amazing. It wasn't even a strong effect. It totally reset the mice into the normal state. They were normal on that diet. There was no deficiencies of any type in them, although they were totally missing the ALDH2 enzyme because they were
Fascinating.
fed on the PUFAs.
Now, were they able to, did they try using it as a therapy for mice that already were starting to show deficits, or it was just entirely preventative?
uh, that model is not terribly amenable for to ask that question because it's like an innate thing. They are born with that,
Okay.
so they gradually develop that thing over time. So we could not. We do not switch it. It's switched on by the fact of conception. Okay, so we do not switch on the phenotype like several
Right, I
months
see what you're
before life.
saying.
So
Well, I
we
mean,
have
you
to
could start giving them DPUFA when they were
a bit later.
older and
Yeah,
they
yeah,
were
yeah.
right.
So
Okay.
not with that study. We did not do that. So I guess you
Okay.
can call that a prevention study. But we do have some studies in which the phenotype appeared first, and then we put the animals on DPUFAs, and then we saw the improvements, mitigation, and reduction of the phenotype. That in different models, like in some retinal diseases, so that the precedents do exist. It doesn't always work that way. We always have like help and mitigation, but such a strong effect, resetting it back to normal, is not doesn't happen that often, and that was the case with the LDH2 animals. I believe you have a paper on that from in your
Yeah,
database.
you sent me a whole bunch of papers.
Yeah.
Thank you. And I'll put those down in the show notes because you've got quite an impressive literature going on this stuff. Um, the what so what do you eat? What do you do to enhance your longevity?
Oh boy.
Or to, shall we say, reduce your to enhance your health span?
Oh, nothing particularly special these days. Let's just cut out the DPUFA element from your question, and on everything else, I I don't overstretch myself. I'm not aware of a single marathon runner who became in his youth, who later became a centenarian. So they say overstretching yourself on that professional level is not really terribly good for longevity. Of course, there are exceptions, but who knows how long he could have lived had he not run or exerted himself that badly. So
Right.
the general understanding is heavy sports or too much of a good thing is not good. Food wise, I kind of I don't have cravings. I don't know. I eat normally. Mostly, I try to eat fish mostly. I do occasionally drink, not every day. Occasionally, don't smoke. So I'm taking my chances with Parkinson's. I suppose maybe I should consider taking.
Yeah.
Yeah, that's it. And trying to keep the brain kind of fresh
Do
by
you try and
reading.
make an effort to avoid vegetable oils or
Oh,
to
I don't. It's either dairy, butter, or olive oils. And as far as olive oils, I always well, I have Tom Brennan at my disposal to consult me. So I
yes,
only
of
ever
course.
pick olive oils which have like almost 80% oleic.
Okay.
Never below that. But although I have to say, to be fair to the mafias who run the vegetable oil markets, to be fair, there is a silent revolution now unfolding, and there is more
Yes.
and more genetically modified things, sunflower, you name it, which actually have an amazingly high rivaling best brands of olive oil, amazingly high oleic acid contents. Those things are actually not bad.
Yes, and thus a low linoleic. I mean, we always,
Yeah,
I think when I was discussing this topic with Tom Brenna, I said, we should call them low linoleic
yeah,
oils, not high
yeah,
oleic oils, because that's really missing the point of what we're trying to accomplish with those things.
yeah.
But yeah, you're right. It is a revolution. They're trying to keep it on the low down. I mean, back to the longevity point, increasing lifespan. I learned 2 years ago from some of the folks I uh, worked with at Zero Acre Farms, which was trying to produce a low linoleic oil, that the Mars company had switched their peanut M&Ms, which was always one of my favorite snacks, from a regular peanut to a low linoleic peanut. And the reason they did that is because the lower lipid peroxidation they saw in that breed of peanut extended the shelf life tenfold.
Yeah, yeah, yeah.
Right? So they were just doing it because it meant they had less wastage. But that means, for me, it means peanut M&Ms are back on my snack list.
By the way, talking of nuts, and I have that table in the book, and I'm only ever looking at things from the lipid peroxidation perspective. There are lots of other aspects which I don't even
Right.
mention,
Yep.
exclusively from lipid peroxidation, food-wise, disease-wise. So I run a table there with fatty acid composition of different nuts.
Hmm.
And what transpired was that the best ones by far, by a huge margin, are macadamia nuts,
Yep.
followed shortly, closely by hazelnuts.
Yep.
And it doesn't look like, because the macadamia essentially is like little gel caps full of oleic acid. There is hardly anything else, just pure oleic acid, better than any olive oil. Hazelnuts have a little bit of linoleic, but mostly it's oleic. But the well-known kind of and highly praised thing called walnuts, they didn't come across all that well because they do have linolenic acid and omega-3, which is in deficiency, but their contents of linoleic is so huge
Right.
that it probably totally eliminates all the benefit from oleic. So, but anyway, it's all in the table. You can take a look if you want.
Yeah, no, it's a great book. I learned a lot from
Thank
it.
you.
Um, and I really enjoyed reading it. And we have to note too that if anybody's going to go buy the book, we highly recommend, or Misha highly recommends, that if you want to read it online, do that, but also buy a copy of the print edition, because there's a little cartoon up in the corner, a flip page animation demonstrating lipid peroxidation and the chain reaction that happens. And I saw the little pictures. I saw little pictures up in the corner, and I didn't realize what they were until you pointed it out to me. But that's a neat little Easter egg in your book. Again, well, Misha, thank you so much for taking the time. It's been a really fascinating
Pleasure,
discussion.
pleasure. Thank you very much. Very entertaining and thought-provoking discussion. It wasn't just an interview. It's you were an equal part of this narration. Thank you very much for your
Oh, that's very
inputs on it.
kind. Thank you. Thank you. No, it's been great.